Hey there, Grant here. So I got to confess, I'm really enjoying making these YouTube videos and the podcast for y'all. So if you also like them, give me a like, give me a subscribe, and send me an email letting me know that you enjoy the topics that I'm covering here. Today, what I want to talk about with y'all is what it's like to learn things in college versus things that you've learned on the job and how they differ from one another. Because I really got to be honest with you, I don't believe that my college degree prepared me for a career in software engineering. There's a whole slew of different things that you need to be effective as a developer in the field than the typical computer science, computer engineering courses that you learn in college. So yes, while I was definitely able to write software and build a working application, I had absolutely no idea how to translate those skills, like those technical hard skills of writing code, into a career of producing a product that could be sold in a market to people who are willing to pay money for it. Two totally different skills. It's like the business of software engineering, which is why we get hired, versus the actual writing of software. So those are the things that I really want to dive into today and talk about with regard to college degree versus real life experience. The first topic that I want to kind of demystify here is algorithmic runtime or asymptotic analysis of algorithms and what that really translates into for the layperson. When you go to college, you're going to learn about algorithmic runtime. And when I talk about this, what I'm really referring to is big O notation, is probably the way you've heard it. There's big O, there's theta, and there's big omega notation. And basically, I'll take all the math and boil this down to a very simple to understand concept. Big O notation just means the worst case runtime of your algorithm. Big omega is best case, and theta is the average case. It's not a perfect analogy there, but it's close enough for the purpose of this video and for practical use of those terms. Because anytime you take a complex idea and boil it into a simple one-liner, you're going to lose nuance. And so I don't really care about losing nuance in this sense. That's really all it means. And I'll give you an example here. So you've got an array of 10 objects or n objects. Doesn't really matter how many are in the container. And you've got a for loop, and you're looking for an item in that container. You're going to iterate over that container n times looking for the thing that you are trying to find. In worst case, big O, you will look through n items. So the algorithm is going to run big O of n times in the worst case to completion. That's really all it means. And so you can compare algorithms to each other using these different notations. To take that a little bit further, if you've got a doubly nested for loop, you're going to run each loop with n items in it. You'll go n times n or n squared. So that algorithm is going to take big O of n squared time, which is going to be longer than big O of n. And you can plot this in a graph and see the curve and how, if you add 1,000,000 items to this, how long is your theoretical runtime going to be? So it helps you gauge the performance of your algorithm. And sometimes this does come in handy. If you are working with trees or search algorithms, you're going to get some weird numbers like n log n or log n runtime or n squared, n cubed, and you can gauge how your application performs and actually run some benchmarks and test it and get some real data and plot these different algorithms against each other to see how they perform. So that's like the math and the science of algorithmic analysis. When you go into the field, though, none of that really matters because what you're trying to do is build a working algorithm before your deadline. And oftentimes, you don't need the most optimal algorithm in order to sell your product or get your product to market. What you need is a working algorithm. And so a lot of times what you'll see is for the first release of an application, you throw in something that'll get the job done, you release your application, and then you spend some time optimizing it and tweaking out that performance, really cranking it down and making your application work super well when you've got some time to focus on making it better instead of just trying to get this thing out to market or add new features. And you can build all these things into your product roadmap, but those are not the things that you learn in college. what you learn in college is all about the algorithmic analysis. And I have a theory on why this is. When you learn about software engineering from someone with a PhD, you're going to get a lot of the academic and the scientific background for software engineering. But when you learn software engineering from a senior developer in the field, you're going to get a lot of the practical experience. And so unless you have somebody who has gone from the field into academia and has built their own course material on how to teach you software engineering, then you're probably going to be lacking in all of this product delivery background or knowledge on how to translate your college degree into a job in the field. And that's okay. This is why internships are actually so important. I did an internship at the end of my sophomore year, and I worked 20 hours a week until I graduated. And that was the most valuable experience for me in college, more so than the actual degree itself. I feel like I only got a job because I had done the internships during college. So I didn't like do a summer internship. I did it all year round until I graduated. And if you can find those, that's legitimately the way to go, is get your internship, get your real world experience in while you're learning in college, and you'll set yourself up for a pretty solid job after college, because you're making network with people in the field. You're already working for a company or multiple companies, so it's really good for you overall. Next, I want to talk with you about tail recursion, for loops, and premature optimization. When I was in college, a lot of what we discussed about our programs was about efficiency and optimization. They put an overemphasis on having a perfect solution, and I can see why that's important in an academic environment. It's like you want to give the 50% solution and turn it in, or the 100% solution. Well, it makes sense to do the 100% solution and turn that into your professor and get graded on it. But when you're in the field, there are sometimes repercussions for having that optimal 100% solution. And here's an example. Recursion is hard. I think it's super hard just to wrap my head around this idea of a function calling itself and going down and down and down and down into a stack of function calls that kind of retain memory and then return back up, and you get, I don't know, it still seems kind of magical to me. It did when I was in college too. It was always really hard for me to wrap my head around the fact that you can convert a for loop to recursion and back again, and that there are performance trade-offs for doing that, and how you calculate a value using these two different methods. And in college, sometimes what you wanted to do, you want to go all in and spend like a week on this problem, determining how to create a recursive loop or recursive function for some problem. But in the field, you don't ever have time to spend a week on an algorithm that's going to be recursive just purely for the sake of performance, unless you're in a very special magical land of product delivery where you've released your application, it's working fine, and you're just cleaning it up, fixing bugs or optimizing it until, I don't know, some new features come around. It's almost always the case that you're going to have a whole lot of new features that you need to build and very little time to get to the to-do cleanup work. So a lot of these optimization problems don't ever come your way unless you're in embedded software engineering, where resources are very difficult to come by and you need optimal, efficient working code. In a typical commercial environment, though, just getting an algorithm that works is the right way to go. And what I mean by that, I had said that sometimes you don't want the 100% solution. And the reason why is because there are maintenance and understanding, knowledge transfer costs associated with that super optimal algorithm. So let's say that for your particular problem, a recursive function is the best way to go about it because, I don't know, something about runtime, right? You can run using your logarithmic analysis. The recursive function will be log n versus an n squared algorithm. Just off the top of my head, I'm making the scenario up, but I think you see where I'm going to with this. Let's say the recursive is better. There's a cost associated with explaining to a new developer on the team how that function works. And the fact that it is recursive means people are going to be a little intimidated to do any bug fixes if there are any bugs in that software or in that piece of code. So you're introducing additional maintenance costs in terms of complexity and fragility of that code. If something were to get passed in, like a null pointer, and you didn't do your null pointer checks, suddenly we're in C++ land here. But you get my point here, that there are going to be bugs in that code that may need to be fixed, and people are going to be hesitant to change anything in a recursive function. If it's just a for loop, then they may not worry about it, dive in there and hack away and try and find these bugs, write some tests, and it'll be a very straightforward thing for them to understand. That's just one scenario. I'm not saying that you want to avoid recursive functions all the time. There's totally a legitimate way to use those in the field, and they're not really all that scary. But in general, what you're trying to do when you're writing software in a commercial environment is get something that works, something that is easily maintainable, something that new people on the team can just pick up and understand, and they're not sitting there scratching their heads for a week trying to figure out this bit of code and how it works. I've certainly found those bits of code in applications that I have been placed in charge of, or that I've inherited from other teams or other people. And it's not really great to sit there and have to figure out how this piece of code works that someone else wrote and is now broken for who knows what reason. So you want to keep it easily maintainable, and that's not something that they talked about in college to me. In college, again, it was all about the optimal solution, the best, the fastest, the smallest memory footprint. And those are very rarely things that I've ever had to consider in my career. And y'all know, I have worked in embedded software engineering. We did consider those problems in that industry, but it wasn't all the time. It was like 10% or less of the times when I was writing software, I had to care about that performance. And in commercial world, I've never had to worry about that at all. There have been a couple of very stellar individuals who did worry about those things and focus on optimizing problems, but they were the exception rather than the rule, and they were always the smartest people on the teams that I have ever worked with. So we're talking one in however many people I've worked with, one in 2,000, one in 5,000 directly that I've worked with. So pretty rare individuals who can do that. And probably my favorite thing here that I've learned in the field that they did not even touch on in college is Agile software development, or literally any software development lifecycle in the entire world. Because in college, we built, I don't know, we built like projects and applications, but we had no delivery process. There was no production environment that we were trying to protect. There was no way of packaging my code up and deploying it out to a place where customers would receive it. It was just, cool, there's my application. It's a jar file or an exe or a binary or a script. It had no delivery processes associated with it. It had no software development processes associated with it either. Oftentimes in college, I was the only person working on the application, or it was me and a small team of like 2 or 3 other people. It was not something that we were building at scale. We did not have 1,000 developers contributing to a piece of code. We did not have a continuous integration, continuous delivery pipeline. We did not have automated testing. Just, it was not at that scale in college. So by the nature of not doing that work, I didn't learn what it was like to actually work on a large software delivery team. When I was in college, Agile was still just emerging onto the scene for the most part too. And so we did learn a little bit about, I think it was called spiral software development, which is a precursor to Agile. It's really you build, test, deploy in a big circle, something like that. I'm a little fuzzy on that because it's been such a long time since I've thought about it. But Agile software delivery is significantly better. And it would have been nice to have learned that there were delivery processes associated with software engineering, and it wasn't just the Wild West where you hack together an application and deploy it. My college did talk about testing. It was not something I was excited about, and so it wasn't a really big part of my college career. Most of my college career focused on learning new technologies, learning data structures, learning algorithms, learning optimization over and over and over again. And it was always at the expense of, how do you sell your application now? How do you package your application so that consumers can get it? How do you release an application when you've got a ton of people working on the same thing at the same time? How do you track bugs? How do you find bugs? How do you fix bugs? Those are all things that I learned in the field, not things that I had learned in college. And it's not the end of the world that I didn't learn these things in college. I would have done just fine if I had graduated and I didn't know any of these things upon graduation. But I'll tell you what, it really set me up to accelerate in my career and do an excellent job on the job by having done an internship in co-ops while I was in college. That is seriously the best thing that I have ever done for myself. And so I would never suggest that you go to college and not do an internship. And not even just the summer internships. I'm talking about year round. Get a job, do freelancing, like actually do the work that you're learning in college in the field. And even if you're going to a boot camp, they're set up slightly differently, and you'll probably learn a little bit more practical experience. Some of the ones that I've seen, they've got an academic portion, and then they've also partnered with big companies, and they'll place their people in the boot camp in the companies for a while. And it's basically like an internship where you'll take stories off of their backlog and deliver real software. And for those of you who are not familiar with the Agile, the backlog is all of the work we have yet to get to. And it's in this thing called a story form, where you mock up as a type of person, I need some sort of a feature so that I can accomplish some sort of work. That's usually the format that they're written in. And a developer will take stories off of this backlog of work to do and then work on those in a 2-week time block. And then that's what will all get packaged up. So every 2 weeks, ideally, real software is being packaged up and delivered. Sometimes it even goes faster than that. I've had some teams work on weekly sprints. I've even had some teams that do daily releases into a production environment. That's what you can get if you go with Agile software development. But you can learn all of these skills as you're getting your degree or as you are learning the experience through boot camp. And I would highly recommend that is the way that you go. Set up your career, learn all the things as early on as you can, because even if you have a 4-year degree, you're not going to know everything that you need to know in order to be an effective software developer in the field. So as I started writing down a list of topics associated with this college education versus in the field education, I realized that it's a subject that I could talk about for hours and hours, things I wish I had learned in college but didn't. And I'm not going to do that. I will probably make some more follow-up videos on this topic, but for now, that is what I wanted to share with y'all. So how does your experience differ from mine? What are some things you wish you had learned in college that you didn't? Or, maybe you went to a boot camp and there are things they didn't teach you that you wish they did. Whatever your path was, I hope it's been effective for you, and I'm sure you've got your own stories. So please share them with me. Drop some in the comments, send me an email. Would love to talk more with you. And as always, don't forget to like and subscribe. We'll see you again next time.